What if the universe was an intricate puzzle, and each piece, from dimensions to atoms, held the key to its existence? Picture it not as a static void, but as a grand symphony where every note, from the tiniest particle to the vastest expanse, plays a role in the cosmic melody. The universe isn't just a place, it's a process, a constant act of creation where dimensions, forces, and matter come together in ways that defy our everyday understanding. To truly grasp how the universe builds itself is to unlock one of the greatest mysteries of all. How did we get here, and what does it all mean? This isn't just a question for scientists or philosophers. It's a journey that touches all of us. From the moment we look up at the night sky and wonder about the stars, to the way we marvel at the complexity of life, we're all connected to this story. But to understand it, we have to start at the very beginning with the forces and structures that shape reality itself. This video will take you on an extraordinary expedition from the explosive birth of the universe in the Big Bang to the delicate dance of atoms that form everything around us. Along the way, we'll explore dimensions that stretch beyond our perception, uncover the quantum realm where the rules of physics seem to bend, and witness the birth of stars and planets that set the stage for life. But this isn't just a story about the universe, it's a story about us. Every atom in your body, every spark of thought in your mind, is a product of this cosmic creation. By the end of this journey, you'll see the universe in a whole new light, not just as something out there, but as something deeply connected to who you are. So let's begin this exploration together and discover how the universe builds itself piece by piece from dimensions to atoms. The Big Bang wasn't just an explosion, it was the beginning of everything. Imagine a single point, unimaginably small and dense, containing all the energy and matter that would eventually become the universe. In a fraction of a second, this point erupted, not into empty space but into space itself. The universe didn't expand into something, it was the something that was expanding. Picture blowing up a balloon, the surface stretches outward, and every point on it moves away from every other point. That's what happened with the universe, but on a scale so vast it's almost impossible to comprehend. In those first moments, the universe was a seething cauldron of energy. Temperatures were so high that particles couldn't form, yet everything was pure energy, a chaotic soup of potential. But as the universe expanded, it began to cool, and that cooling allowed the first particles to emerge. Think of it like steam condensing into water droplets. That's when the universe started to take shape, with the fundamental forces gravity, electromagnetism, and the strong and weak nuclear forces beginning to carve out the rules of reality. The Big Bang wasn't just a moment, it was a process, a cascade of events that set the stage for everything we see today. It created the framework for dimensions to exist, for particles to form, and for forces to govern how those particles interact. Without that initial burst of energy, there would be no stars, no planets, no life. It's the starting point of the cosmic story, the foundation on which everything else is built. But here's the question: how did this explosive beginning lead to the intricate, structured universe we observe now? How did chaos give way to order? Dimensions are the invisible scaffolding of reality, the framework within which everything exists and moves. We're all familiar with the three dimensions of space: length, width, and height. These are the axes that define how objects interact with one another, from the way a ball bounces to the orbits of planets. Imagine a graph in mathematics, where each axis represents a dimension. Without these axes, you couldn't plot a point or describe a shape. The same logic applies to the universe. Dimensions provide the structure that allows physical phenomena to occur, from the smallest particles to the largest galaxies. But what if there are more dimensions than the ones we can see? This is where string theory enters the picture, proposing the existence of additional, hidden dimensions. While we can't directly perceive these extra dimensions, they might play a crucial role in the behavior of particles and the forces that govern them. Think of it like a piece of paper. From a distance, it appears flat, two-dimensional, but up close, you might notice tiny ripples or textures that hint at a third dimension. In the same way, extra dimensions could be curled up or compacted at such a small scale that we can't detect them, yet they might influence the fabric of reality in profound ways. Dimensions aren't just abstract concepts, they shape how we experience the world. Without them, the universe would be a formless void, lacking the structure needed for stars to shine, planets to form, or life to exist. They're the stage on which the cosmic drama unfolds, but here's the intriguing question. If dimensions provide the framework, what fills that space? What exists within these dimensions to create the richness and complexity of the universe we see around us? Time is the silent orchestrator of the universe, the fourth dimension that weaves together the fabric of reality. While space gives us the stage, time provides the flow, the narrative that allows events to unfold. Imagine a river endlessly moving forward, carrying everything in its current. This is how time operates, always advancing in one direction, shaping the past, present, and future. Unlike the dimensions of space, time feels intangible, yet its influence is everywhere. It's the reason we see stars age, planets orbit, and life evolve. Without time, the universe would be frozen, a static snapshot without motion or change. But time isn't just a passive observer, it's deeply intertwined with space, forming what physicists call spacetime. This concept, central to Einstein's theory of relativity, reveals that space and time are not separate entities but part of a single, interconnected system. Think of spacetime as a vast, flexible sheet. Massive objects like stars and planets create curves in this sheet, altering the flow of time around them. This is why time moves slower near a black hole than on Earth. Gravity warps the fabric of spacetime itself. It's a mind-bending idea, but one that reshapes our understanding of how the universe operates. Time also plays a crucial role in the universe's evolution. From the Big Bang to the formation of galaxies, time has been the driving force behind every cosmic event. It's the dimension that allows processes to unfold, from the collision of particles to the birth of stars. Without time, there would be no cause and effect, no history or future. It's the glue that binds the universe's story together. But here's the question: how do space, time, and the other dimensions interact to create the building blocks of existence? What happens when these forces come together in the quantum realm? The quantum realm is where the ordinary rules of the universe dissolve, and reality takes on a surreal, almost magical quality. Here, at the tiniest scales imaginable, the familiar dimensions of space and time blur, and particles behave in ways that defy common sense. This is the domain of quantum mechanics, the science of the very small, where particles can exist in multiple states at once, pass through barriers, and instantaneously influence each other across vast distances. It's a world where the impossible becomes routine, and our everyday understanding of reality is turned upside down. One of the most baffling phenomena in the quantum realm is superposition, the idea that a particle can exist in multiple states simultaneously until it's observed. Imagine a coin spinning in the air. It's neither heads nor tails, but both at the same time. Only when it lands does it settle into one state. In the quantum world, particles like electrons can exist in a superposition of positions, speeds, or even energies until they're measured. This strange behavior isn't just theoretical. It's the foundation of technologies like quantum computers, which harness superposition to perform calculations far beyond the reach of classical machines. Then there's entanglement, a phenomenon so bizarre that even Albert Einstein called it spooky action at a distance. When two particles become entangled, their properties become linked, no matter how far apart they are. Change one particle, and the other instantly responds, as if they share a hidden connection that transcends space and time. This isn't science fiction. It's been repeatedly demonstrated in experiments, and it suggests that the quantum realm operates on a level of interconnectedness that challenges our understanding of reality. The quantum realm isn't just a curiosity. It's a bridge between the abstract dimensions of space and time and the tangible particles that make up the universe. In the chaotic aftermath of the Big Bang, the quantum fluctuations that rippled through space laid the groundwork for the formation of matter. These tiny irregularities, magnified by the universe's expansion, seeded the first structures, galaxies, stars, and planets. Without the quantum realm, the universe as we know it wouldn't exist. But for all its strangeness, the quantum realm is also a place of profound beauty and potential. It's where the fundamental forces of nature emerge, shaping the behavior of particles and the destiny of the cosmos. It's a reminder that the universe is far more intricate and mysterious than we can imagine, a tapestry woven from the threads of space, time, and probability. Within this quantum realm, particles emerge, but where do they come from? What is the source of the energy that gives rise to matter, and how does it shape the universe we inhabit? In the fiery aftermath of the Big Bang, the universe was a cauldron of pure energy, a seething, chaotic expanse where the laws of physics were still taking shape. Amid this cosmic turbulence, something extraordinary happened. Energy began to transform into matter. This process, known as pair production, is one of the most fundamental events in the history of the universe. Imagine a roaring fire, its heat and light radiating outward. Suddenly, sparks fly from the flames, each one a burst of energy igniting into something tangible. In the early universe, something similar occurred, but on a scale far grander and more mysterious. Pair production happens when a photon, a packet of pure energy, interacts with a strong electromagnetic field, creating a particle and its antimatter counterpart. Picture it like a coin split into two halves. One becomes matter, the other antimatter. This process didn't just happen once. It occurred countless times in the early universe's dense, energetic environment, filling the cosmos with the first particles. But here's the twist: matter and antimatter are like opposites. When they meet, they annihilate each other, returning to pure energy. So why didn't the universe destroy itself in a blaze of mutual annihilation? The answer lies in a tiny, unexplained imbalance, a slight excess of matter over antimatter. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That one extra particle was enough to seed the entire universe with the matter we see today. This transformation from energy to matter wasn't just a fleeting event, it was the foundation of everything that followed. Without it, there would be no stars, no planets, no life, just an empty void. The particles born in this process were the first building blocks of the universe, the seeds from which all structure would grow. They were simple at first: quarks and electrons, the most basic pieces of the cosmic puzzle. But these humble beginnings held the potential for everything we know, from the atoms in our bodies to the galaxies spinning in the night sky. The birth of particles also marked the universe's first steps toward complexity. As it expanded and cooled, these particles began to interact, drawn together by the fundamental forces of nature. Gravity, the weakest but most far-reaching of these forces, started to pull matter into clumps, setting the stage for the formation of stars and galaxies. The strong force operating at the tiniest scales bound quarks together to form protons and neutrons, and the electromagnetic force with its push and pull governed the behavior of charged particles, shaping the structure of atoms. But how did these particles come together to form the atoms we know today? How did the chaotic energy of the early universe give rise to the ordered structures that make up our world? The answer lies in the delicate dance of forces and particles, a cosmic choreography that began in the first moments of existence and continues to shape the universe to this day. In the swirling chaos of the early universe, just moments after the Big Bang, the first particles began to take shape. These weren't the atoms we know today, no. These were the most basic building blocks of matter, the quarks and leptons that would eventually form everything from stars to planets to life itself. Picture the universe as a massive, hot soup bubbling with energy. In this environment, quarks and leptons emerged like tiny specks floating in a cosmic broth. Quarks are the particles that make up protons and neutrons, while leptons include familiar particles like electrons. Together, they form the foundation of all matter. But how did these particles come into existence? In the unimaginable heat of the early universe, energy was so intense that it could spontaneously convert into matter. Think of it like water boiling in a pot where bubbles rise to the surface and burst. In the same way, particles popped into existence from the energy of the universe, only to collide and interact in a frenzied dance. Quarks, in particular, are never found alone in nature. They always come in groups of 2 or 3, bound together by the strong force, a fundamental force of nature that acts like an invisible glue. Leptons, on the other hand, are more independent. The most well-known lepton is the electron, a particle that orbits the nucleus of an atom. But there are other types of leptons too, like muons and tau particles, each with their own unique properties. Together, quarks and leptons form a sort of cosmic toolkit, with each particle playing a specific role in the construction of the universe. It's like assembling a puzzle where every piece has its place. Quarks combine to form protons and neutrons, which then join with electrons to create the first atoms. But this process didn't happen all at once. It took time, and the universe had to cool down enough for these particles to start coming together. The formation of quarks and leptons was a critical step in the universe's evolution. Without them, there would be no protons, no neutrons, no atoms, no structure at all. These particles are the alphabet of the cosmos, the letters that combine to form the words and sentences of the universe's story. And just as a sentence can convey a powerful idea, the combination of quarks and leptons gave rise to the complexity we see today. With these fundamental particles in place, the universe was ready to take the next step, combining them into more complex structures like protons and neutrons, which would eventually form the nuclei of atoms. In the heart of every atom lies a force so powerful yet so precise that it holds the very fabric of matter together. This is the strong force, one of the 4 fundamental forces of nature, and it's the glue that binds quarks into protons and neutrons. Unlike gravity, which works across vast distances, the strong force operates at an incredibly tiny scale, reaching only about the width of a single proton. But within that range, it's unimaginably strong, about 100 times more powerful than the electromagnetic force that holds atoms together. Picture it like a supercharged magnet, but one that only works when particles are almost touching. If you tried to pull quarks apart, the strong force would pull them back together with a force that grows stronger the farther they get, like an unbreakable elastic band. What makes the strong force truly remarkable is how it shapes the stability of atomic nuclei. Without it, that protons and neutrons wouldn't stay bound together and atoms couldn't exist. Imagine trying to build a house without nails or glue. Everything would fall apart. In the same way, the strong force ensures that protons and neutrons stick together, despite the fact that protons, which are positively charged, would normally repel each other due to their electric charge. It's this delicate balance between the strong force and the electromagnetic force that allows atoms to remain intact, forming the stable building blocks of matter. The strong force also plays a critical role in the creation of elements. Inside stars, where temperatures and pressures are extreme, protons and neutrons are squeezed together to form heavier elements like helium, carbon, and oxygen. This process, known as nuclear fusion, is powered by the strong force which binds these particles into new configurations. It's like a cosmic forge where the strong force acts as the blacksmith's hammer, shaping the raw materials of the universe into more complex forms. But how does such an intense force work? The strong force is carried by particles called gluons, which act like messengers, shuttling between quarks and keeping them bound. Think of gluons as the couriers of the subatomic world, constantly delivering the glue that holds quarks together. And because quarks come in different flavors, the interactions between them can be incredibly complex, like a dance where the steps are constantly changing. This complexity is part of what makes the strong force so fascinating. It's not just a simple tug of war, but a dynamic interplay that shapes the very structure of matter. The strong force is a reminder of how finely tuned the universe is. It's a force that works behind the scenes, hidden from our everyday experience, yet it's essential for the existence of everything we see around us. Without it, the universe would be a chaotic sea of unbound quarks, unable to form the stars, planets, and life we know today. So, with particles bound together by this incredible force, what was the next step in building the universe? In the early universe, just moments after the Big Bang, the first atoms began to take shape. But it wasn't a simple process, it was the result of countless interactions between the simplest particles. Protons and neutrons, bound together by the strong force, started to combine in pairs and triplets. The most basic of these combinations formed the nuclei of hydrogen and helium, the very first elements. Hydrogen, the simplest atom, consists of just a single proton orbited by an electron. Helium, slightly more complex, has 2 protons and 2 neutrons in its nucleus, with 2 electrons circling around it. These elements may seem basic, but they were the foundation of everything that would come later, the building blocks of stars, galaxies, and even life itself. The creation of these atoms occurred during a period called Recombination, which happened roughly 380,000 years after the Big Bang. Before this, the universe was far too hot for atoms to form. Electrons zipped around freely, colliding with protons and neutrons in a chaotic, seething plasma. But as the universe expanded and cooled, the energy levels dropped just enough for electrons to settle into stable orbits around nuclei. This marked the birth of the first atoms, and for the first time, light could travel freely through space without being scattered by free electrons. This event is often referred to as the universe's first light, and it's the source of the cosmic microwave background radiation we can still detect today. Hydrogen and helium didn't just appear randomly, they were the natural outcome of the universe's early conditions. The Big Bang produced a precise ratio of particles. For every neutron, there were about 7 protons. This ratio determined the abundance of these elements. About 75% of the universe's mass became hydrogen, while 25% became helium. Trace amounts of lithium also formed, but these first 2 elements dominated the cosmic scene. This primordial mixture of hydrogen and helium set the stage for the universe's chemical evolution, like the first strokes of paint on a blank canvas. The periodic table, which we often think of as a collection of over 100 elements, started with just these two. Hydrogen, at the top left of the table, is the most abundant element in the universe, while helium sits right next to it. Their simplicity belies their importance. Hydrogen, with its single proton, is the fuel that powers stars, while helium, with its stable nucleus, plays a key role in stellar fusion processes. Together, they formed the raw materials for the first stars and galaxies, igniting the cosmic processes that would eventually lead to the creation of heavier elements, planets, and even life. With these first atoms in place, the universe was no longer a featureless soup of particles. It had structure, and it was ready to take the next step. But how did these atoms come together to form stars and galaxies? Gravity is the invisible architect of the universe, the force that quietly but relentlessly shapes everything we see. After the formation of the first atoms, gravity stepped in to orchestrate the next act of cosmic creation. It's easy to think of gravity as just the force that keeps us grounded, but its role on the cosmic stage is far more profound. Imagine a spiderweb stretching across a vast expanse, each thread representing the pull of gravity. Wherever matter gathered, however slightly, gravity began to tug, drawing more material into those regions. Over time, these tiny clumps grew denser and denser, like snowballs rolling downhill, gathering mass as they went. This process, known as gravitational collapse, is what allowed the universe to transform from a nearly uniform sea of hydrogen and helium into the intricate tapestry of stars and galaxies we see today. The early universe was filled with tiny fluctuations in density, leftover ripples from the Big Bang itself. These fluctuations might have been minuscule, but gravity amplified them, turning small differences into enormous structures. Picture a flat sheet of paper with a few faint creases. Gravity pressed down on those creases, deepening them until they became folds, and eventually mountains. In much the same way, gravity took those faint ripples in the cosmos and sculpted them into the first stars and galaxies. As matter clumped together, the gravitational pull became stronger, creating a feedback loop that accelerated the process. What began as a whisper of attraction grew into a cosmic roar, shaping the universe on an unimaginable scale. But gravity's influence didn't stop there. As the universe continued to expand, gravity worked on two fronts, pulling matter together on small scales while simultaneously shaping the large-scale structure of the cosmos. On one level, it drew gas and dust into dense clouds that would ignite as stars. On another, it wove those stars into galaxies, and galaxies into clusters, filaments, and voids, forming the cosmic web that spans the universe. This web is like a three-dimensional map of gravity's handiwork, with galaxies clustered along its threads like beads on a string, and vast empty spaces, cosmic voids, where gravity's pull was weaker. One of gravity's most remarkable feats was creating the conditions for stars to ignite. As clouds of hydrogen and helium grew denser, the pressure and temperature at their cores increased. When these conditions reached a critical point, nuclear fusion began and a star was born. This process didn't just light up the universe, it also forged the heavier elements that would later form planets, life, and us. Gravity's role as the master builder didn't end with the birth of stars either. It continues to shape the universe today, from holding galaxies together to guiding the orbits of planets. But how did gravity create the conditions for the birth of stars? To understand that, we need to dive into the heart of cosmic clouds, where the seeds of stars are sown. Deep within the vast clouds of hydrogen and helium that drifted through the early universe, the seeds of stars began to take shape. These cosmic nurseries, often called molecular clouds, were the birthplaces of the first stars. Picture these clouds as immense dark factories, cold and dense, where gravity worked like an unseen hand, slowly gathering material into tighter and tighter clumps. As these clumps grew, their gravitational pull increased, drawing in more gas and dust. Over time, the pressure and temperature at the core of these collapsing clouds rose dramatically, like a knot tightening in a piece of string. When the core temperature reached around 10 million degrees Celsius, something extraordinary happened. Nuclear fusion ignited. At this moment, hydrogen atoms began fusing together to form helium, releasing an enormous amount of energy in the process. This energy counteracted the force of gravity, creating a delicate balance that allowed the young star to shine steadily. It's like a forge in the cosmos, where raw materials are transformed into something entirely new. But stars are more than just glowing orbs of gas. They are cosmic factories, tirelessly churning out heavier elements. As fusion continues, helium atoms fuse to form carbon, and carbon to form oxygen, and so on, all the way up to iron in the cores of the most massive stars. This process is a slow but relentless alchemy, transforming the simplest elements into the building blocks of planets, life, and even us. Every atom of oxygen we breathe, every speck of carbon in our bodies, was forged in the heart of a star. These elements are scattered into space when stars die, enriching the cosmos with the ingredients for future generations of stars and planets. It's a cycle of creation and destruction that has shaped the universe for billions of years. The birth of a star is not just a solitary event, it's a cosmic phenomenon that ripples across the universe, influencing everything around it. The intense radiation and stellar winds from newborn stars can compress nearby gas, triggering the formation of even more stars. In this way, stars are not just products of the universe but also its architects, shaping the environments that give rise to new generations of stellar life. But as awe-inspiring as this process is, it's only the beginning of a star's story. For every star that ignites, there comes a moment when its fuel runs out and its journey takes a dramatic turn. What happens next is one of the most spectacular events in the cosmos. When a star exhausts its nuclear fuel, its fate depends on its size. For the most massive stars, the end is nothing short of spectacular. As fusion slows and the outward pressure weakens, gravity takes over, collapsing the star's core in a matter of seconds. This sudden collapse triggers a cataclysmic explosion known as a supernova. Imagine the energy of billions of stars unleashed in an instant, lighting up the cosmos with unimaginable brightness. In that fleeting moment, temperatures soar to over 100 billion degrees, creating conditions so extreme that new elements are forged in the heart of chaos. Elements like gold, silver, and uranium, which cannot form in the gentle fusion processes of a living star, are born in these violent explosions. The force of a supernova is so immense that it flings these newly formed elements across vast distances, scattering them into the surrounding space. This cosmic debris, enriched with heavy elements, mingles with the gas and dust of the interstellar medium. Over time, gravity begins to pull these materials together, forming clouds where new stars and planets can take shape. It's a cycle of destruction and creation where the death of one star gives life to countless others. Every atom of iron in our blood, every speck of calcium in our bones, and every trace of gold in our jewelry was once part of a star that exploded billions of years ago. But the story doesn't end there. These scattered elements don't just float aimlessly through the void. They become the raw materials for new celestial bodies. In the aftermath of a supernova, the shockwaves compress surrounding gas, triggering the birth of new stars. These stars, in turn, are surrounded by disks of material that clump together to form planets, moons, and asteroids. The carbon in our DNA, the oxygen we breathe, and the silicon in the Earth's crust all owe their existence to the remnants of ancient stars. In this way, supernovae are not just endings, they are the catalysts for new beginnings. The process of stellar death and element creation is a testament to the interconnectedness of the universe. It's a reminder that even in the vastness of space, nothing exists in isolation. The elements forged in the hearts of stars travel across galaxies, becoming part of new worlds and eventually part of us. This cosmic recycling is a story of transformation, where the remnants of the past become the building blocks of the future. But how did these elements scattered across the cosmos come together to form the planets we call home? The scattered remnants of supernova, rich with heavy elements, drift through the vastness of space, waiting for the forces of gravity to bring them together. Over millions of years, these particles begin to gather, drawn by the invisible pull of mutual attraction. Picture a snowball rolling down a hill, gathering more snow as it moves. This is the process of accretion, where tiny particles collide and stick together, growing larger over time. In the cold, dark regions of space, this process is the first step in building the worlds we call planets. As these clumps of material grow, their gravitational pull becomes stronger, attracting even more gas and dust. In the swirling disks of debris surrounding young stars, these growing bodies begin to take shape. Depending on their distance from the star and the materials available, they evolve into different types of planets. Closer to the star, where temperatures are high, volatile materials like water and methane evaporate, leaving behind dense, rocky worlds like Earth and Mars. Farther out in the cooler regions of the disk, gas giants like Jupiter and Saturn form, their massive atmospheres composed mostly of hydrogen and helium. The process is chaotic and dynamic, with collisions and mergers shaping the final form of these worlds. Think of a construction site where materials are constantly being added, rearranged, and sometimes removed. This is the environment in which planets are born. Over time, the most stable bodies emerge, their surfaces and atmospheres shaped by their composition, distance from the star, and interactions with other objects. Some become barren, rocky worlds, while others grow into swirling giants with thick atmospheres and countless moons. But among this diversity, a few planets stand out, worlds like Earth, where conditions are just right for life to take hold. It's a delicate balance shaped by countless factors: the right distance from the star to maintain liquid water, a protective atmosphere to shield against harmful radiation, and a stable climate to foster the development of complex molecules. These worlds are rare gems in the cosmic ocean, their formation a testament to the intricate dance of forces that govern the universe. Yet, even with all the pieces in place, the journey from a lifeless rock to a thriving planet is far from simple. What made Earth and perhaps other worlds capable of supporting life? As the early Earth cooled and its surface stabilized, a remarkable transformation began to unfold. The elements forged in the hearts of stars, carbon, hydrogen, nitrogen, oxygen, and more, started to interact in ways that would set the stage for something extraordinary. In the vast oceans and volcanic pools of our young planet, these simple elements began to bond, forming increasingly complex molecules. Water, that most essential of compounds, played a crucial role, acting as a solvent that allowed these molecules to mix and react in countless ways. Imagine a vast chemical laboratory where the ingredients of life are stirred and heated, waiting for the right conditions to spark something new. Among the most important of these complex molecules were amino acids, often referred to as the building blocks of life. These compounds, formed through the interaction of carbon, hydrogen, oxygen, and nitrogen, are the foundation of proteins which perform countless functions in living organisms. The famous Miller-Urey experiment in the 1950s demonstrated that amino acids could form under conditions thought to mimic the early Earth, providing a glimpse into how life's ingredients might have arisen. Picture a lightning storm over a primordial ocean, where the energy from the strikes drives chemical reactions that create these vital molecules, but amino acids are just the beginning. Over time, these molecules began to link together, forming longer chains called peptides and eventually proteins. At the same time, other essential molecules, such as nucleotides, began to emerge. These are the building blocks of DNA and RNA, the molecules that carry the genetic instructions for all known life. The formation of these complex molecules was a slow, step-by-step process, driven by the chemical interactions of their simpler components. It's like assembling a puzzle where each piece fits perfectly with the others, gradually revealing the bigger picture. The presence of water was essential to this process, not just as a solvent but as a medium that allowed these molecules to move, interact, and evolve. Water's unique properties, its ability to dissolve a wide range of substances, its role in chemical reactions, and its ability to maintain stable temperatures, made it the perfect cradle for life's emergence. Without water, the complex chemistry that led to life as we know it might never have occurred. Yet the question remains, how did these molecules, complex as they were, come together to form the first living cells? The transition from chemistry to biology is one of the greatest mysteries in science, a leap that required not just the right molecules but the right conditions, energy sources, and perhaps even a bit of cosmic luck. What sparked the first self-replicating molecules, the first cells, and the first signs of life on our planet? From the swirling chaos of complex molecules, a remarkable transformation began to take place. Imagine a bustling kitchen where ingredients are mixed, heated, and combined to create something entirely new. In the same way, the molecules of the early Earth amino acids, nucleotides, and others started to interact in ways that would lead to the first living cells. This process, however, wasn't a single event but a gradual, step-by-step journey driven by chemical reactions and the relentless forces of natural selection. Some molecules proved more stable or better at replicating than others, and over time these advantageous traits became more common, paving the way for life's emergence. One of the key players in this story is RNA, a molecule that can both store genetic information and catalyze chemical reactions. Scientists believe that RNA, or something similar, may have been the first self-replicating molecule, a bridge between simple chemistry and the complex machinery of life. Picture a loop of RNA floating in a warm, nutrient-rich pool, copying itself over and over, each iteration slightly different from the last. These variations, driven by random mutations, allowed some RNA molecules to become more efficient at replication, setting the stage for the first rudimentary forms of life. Another crucial factor was the presence of energy sources, such as sunlight, volcanic heat, and chemical reactions in the environment. These energy sources provided the fuel needed to drive the chemical reactions that built complex molecules and eventually cells. Think of a campfire that keeps a pot of soup simmering without that energy. The molecules would remain inert, unable to form the structures necessary for life. In the oceans and hydrothermal vents of the early Earth, this energy was abundant, creating the perfect conditions for life to take hold. Water, too, played an indispensable role, acting as both a solvent and a medium for chemical reactions. Its ability to dissolve a wide range of substances allowed molecules to mix and interact in ways that wouldn't have been possible in a dry environment. Water also helped regulate temperature, providing a stable environment where delicate chemical processes could occur. It's like a conductor in an orchestra, ensuring that all the instruments play in harmony to create a beautiful symphony. As these molecules became more complex, they began to organize themselves into structures that could carry out the functions of life. The first cells were likely simple, enclosed by a membrane that separated them from their environment. These membranes, made of lipids, acted like tiny bubbles, protecting the delicate chemistry inside while allowing nutrients to enter and waste to exit. Over time, these early cells developed more sophisticated mechanisms for energy production, replication, and adaptation, setting the stage for the incredible diversity of life we see today. This transformation from molecules to cells was a monumental leap, one that took millions of years to unfold. It's a story of trial and error, of molecules interacting in countless ways until the right combinations emerged. And yet, this is just the beginning of life's journey. From these simple beginnings, life would go on to evolve into a breathtaking array of forms, each shaped by the forces of natural selection and the challenges of a changing world. So how did life evolve to become the diversity we see today? Life's journey from single-celled simplicity to the astonishing diversity of complex organisms is a story of relentless adaptation and innovation. Picture a single-celled organism floating in the ancient oceans, its existence governed by the simple tasks of feeding, growing, and dividing. Over billions of years, these humble beginnings gave rise to an intricate tapestry of life, shaped by countless interactions between genetic mutations, environmental pressures, and the unstoppable march of time. Genetic mutations, often random and unpredictable, acted as the raw material for evolution. Some mutations were harmful, causing cells to malfunction or die, while others provided advantages, allowing organisms to survive and reproduce more effectively. These beneficial changes, when passed down through generations, became the building blocks of evolution. Environmental pressures played a crucial role in determining which traits were advantageous. In a world where resources were often scarce and dangers abundant, organisms had to adapt or perish. For instance, in the early oceans, some cells developed the ability to photosynthesize, harnessing the sun's energy to produce food. This innovation not only helped these cells thrive, but also transformed the Earth's atmosphere, paving the way for more complex life forms. Over time, organisms evolved new ways to navigate their environments, from the development of fins and limbs for movement to the evolution of senses like sight and hearing. The eye, for example, is a marvel of biological engineering. Starting as a simple light-sensitive patch in some early organisms, it gradually evolved into the complex, image-forming structures we see in animals today. This process wasn't a straight path but a branching tree of trial and error, with countless variations and dead ends along the way. Time, the silent architect of evolution, allowed these changes to accumulate. What might seem like minor adaptations over a few generations could lead to dramatic transformations over millions of years. Consider the transition from water to land, a monumental shift in life's history. Early fish-like creatures developed lungs and sturdy limbs, enabling them to venture onto land. These pioneers gave rise to amphibians, reptiles, and eventually mammals, each group adapting to new environments and challenges in unique ways. The evolution of flowering plants is another remarkable example. By developing flowers to attract pollinators, these plants formed intricate relationships with insects, birds, and other animals, reshaping entire ecosystems. Through these processes, life became more diverse and interconnected. Predators and prey evolved in a constant arms race, each driving the other to new heights of specialization. Plants developed defenses against herbivores, while herbivores evolved ways to overcome these defenses. Every niche in the environment became filled with organisms uniquely suited to thrive there. This ever-changing dance of adaptation and survival has shaped the world we inhabit, from the lush rainforests to the vast savannas, from the depths of the oceans to the highest mountain peaks. So, how did life's evolution shape the world we inhabit? It's a story of resilience, creativity, and the extraordinary power of small changes over time. Earth stands as a rare gem in the vast expanse of the cosmos, a planet uniquely equipped to nurture and sustain life. Its story begins with its position in the solar system, orbiting the Sun at just the right distance, what scientists call the Goldilocks zone. Not too close where scorching heat would vaporize water, and not too far where freezing temperatures would turn it to ice. This perfect balance allows liquid water to exist, the essential ingredient for life as we know it. But Earth's advantage doesn't end there. Its atmosphere, a delicate blend of gases, acts as both a shield and a nurturer. The ozone layer absorbs harmful ultraviolet radiation, protecting life from the sun's harshest effects, while oxygen, nitrogen, and trace gases create a breathable environment for countless organisms. Another critical factor is Earth's magnetic field, generated by the swirling molten iron in its core. This invisible force deflects charged particles from the sun, preventing them from stripping away the atmosphere and exposing the surface to deadly radiation. Without this protective barrier, life as we know it would struggle to survive. Earth's geology also plays a pivotal role. The movement of tectonic plates recycles nutrients, shapes continents, and drives volcanic activity, which in turn releases gases that help regulate the atmosphere. This dynamic interplay between the planet's surface and its interior creates a stable yet ever-changing environment, one that has allowed life to adapt and thrive over billions of years. Water, though, is perhaps Earth's most defining feature. It covers more than 70% of the planet's surface, creating vast oceans that moderate temperatures and support an incredible diversity of life. From the tiniest plankton to the largest whales, the oceans are teeming with organisms that form the foundation of Earth's ecosystems. On land, freshwater rivers and lakes provide habitats for countless species, while rain and snow cycle water through the atmosphere, nourishing forests, grasslands, and deserts. This intricate water cycle ensures that life can flourish in even the most remote corners of the planet. Earth's moon, too, plays a crucial part in its story. The moon's gravitational pull creates the tides which have shaped coastlines and influenced the evolution of marine life. It also stabilizes Earth's axial tilt, preventing extreme shifts in climate that could make the planet uninhabitable. Together, these factors create a delicate harmony, a web of conditions that, as far as we know, exists nowhere else in the universe. Yet, Earth's story is not just about its physical attributes. It's also about time, the billions of years it took for life to emerge, evolve, and transform the planet. From the first single-celled organisms to the complex ecosystems we see today, Earth has been a stage for the grand drama of life. But how does Earth's story fit into the broader universe? The cosmos is not a random scattering of stars and galaxies, but a carefully woven tapestry, a structure so vast and intricate that it defies imagination. This is the cosmic web, the universe's large-scale architecture. Picture it as a spider's web, but on an almost incomprehensible scale. Instead of silken threads, this web is made of dark matter and galaxies, stretching across billions of light years. At its heart are the filaments, long, winding strands that connect clusters of galaxies like highways of light and gravity. Between these filaments lie vast, empty regions known as voids, where matter is sparse and darkness reigns. Together, these filaments and voids form a network that shapes the universe's evolution. Gravity is the master weaver of this cosmic web. In the early universe, tiny fluctuations in density, remnants of the Big Bang, began to pull matter together. Over billions of years, gravity amplified these differences, drawing more and more matter into dense regions while leaving others nearly empty. Dark matter, an invisible and mysterious substance that makes up most of the universe's mass, played a crucial role. Its gravitational pull guided ordinary matter, the stuff of stars and galaxies, into the filaments we see today. Without dark matter, the cosmic web as we know it would not exist. This structure is more than just a static framework. It's a dynamic system, constantly evolving as galaxies move along the filaments, pulled by gravity's unrelenting force. Clusters of galaxies form at the intersections, where the densest concentrations of matter create hubs of cosmic activity. These clusters are the universe's metropolises, bustling with stars, gas, and dark matter. Yet, even within this vast network, there's a surprising order. The distribution of galaxies and clusters follows patterns that scientists can study and map, revealing the underlying blueprint of the universe. The cosmic web also plays a critical role in the universe's ongoing story. It acts as a scaffold for the formation of galaxies, guiding the flow of gas and dust into regions where stars can ignite and planets can form. Without this structure, the universe would be a far less hospitable place, with matter scattered thinly and irregularly. The web's filaments and voids influence everything from the birth of stars to the expansion of the cosmos itself. What role does this structure play in the universe's ongoing evolution? Dark matter and dark energy are the universe's most elusive and mysterious components, yet they make up the vast majority of its contents. Think of them as the unseen hands that shape and propel the cosmos. Dark matter, though invisible, exerts a powerful gravitational pull, weaving the cosmic web and holding galaxies together. Without it, stars and galaxies would fly apart, and the universe would look vastly different. Dark energy, on the other hand, is the force driving the universe's accelerated expansion, acting like an invisible pressure pushing everything apart at an ever-increasing rate. Together, these two hidden forces govern the universe's structure and fate. Dark matter's influence is most evident in the way galaxies behave. When astronomers study the rotation of galaxies, they find that stars on the outer edges move just as fast as those near the center. This defies the laws of gravity based on visible matter alone. The only explanation is the presence of dark matter, an invisible halo surrounding galaxies and providing the extra gravitational pull needed to keep them intact. It's like a cosmic glue binding galaxies together and shaping the filaments of the cosmic web. Without dark matter, the universe's intricate structure would unravel. Dark energy, meanwhile, is even more enigmatic. Discovered in the late 1990s through observations of distant supernova, dark energy appears to be counteracting gravity itself. While gravity pulls matter together, dark energy works on the largest scales to push the universe apart. Imagine a balloon that not only inflates but does so faster and faster over time. This is the effect of dark energy, and it's reshaping our understanding of the cosmos. Scientists estimate that dark energy makes up about 68% of the universe, while dark matter accounts for another 27%, leaving just 5% for the ordinary matter we can see and touch. The interplay between these forces is a cosmic tug-of-war. Dark matter's gravity draws matter into clusters and filaments, while dark energy stretches the fabric of spacetime, creating vast voids. This dynamic balance shapes the universe on the grandest scale, influencing everything from the distribution of galaxies to the fate of the cosmos. Yet, despite their critical roles, both dark matter and dark energy remain shrouded in mystery. What are they made of? How do they interact with the forces we understand? These questions drive some of the most exciting research in modern astrophysics. One of the most intriguing theories about dark matter suggests it could be composed of exotic particles that interact with ordinary matter only through gravity, making them nearly impossible to detect. Experiments deep underground and in space are searching for these elusive particles, hoping to shed light on one of the universe's greatest puzzles. Dark energy, on the other hand, might be a property of space itself, a form of energy inherent to the vacuum of the cosmos. This idea, rooted in Einstein's theory of general relativity, raises profound questions about the nature of spacetime and the ultimate fate of the universe. As we continue to probe these hidden forces, we are not just uncovering the secrets of the cosmos, but also confronting the limits of our understanding. The study of dark matter and dark energy challenges us to rethink the fundamental laws of physics and our place in the universe. How do these mysterious components influence the universe's future, and what does their existence mean for the ultimate destiny of everything we know? The fate of the universe is a topic that stretches the boundaries of our imagination, shaped by two powerful forces, expansion and entropy. Picture the universe as an ever-growing canvas, stretching wider and wider as dark energy continues to push galaxies apart. Over billions of years, this expansion will accelerate, causing galaxies to drift farther and farther away from one another. The stars within them will burn out, and the universe will grow colder and darker. This scenario, known as the Big Freeze, paints a picture of a universe that slowly fades into a vast, empty expanse, where even the light from distant stars can no longer reach us. Entropy, the relentless tendency toward disorder, plays a crucial role in this process. Imagine a clock winding down, its gears grinding to a halt. Entropy works in a similar way, gradually breaking down the organized structures in the universe. Stars exhaust their fuel, planets crumble, and even black holes eventually evaporate over incomprehensible timescales. In the end, the universe could reach a state of maximum entropy, known as heat death, where all energy is evenly distributed and no work can be done. It's a quiet, still end where even the echoes of the Big Bang have long since faded. But what does this mean for the universe's building blocks? As the universe expands, the very fabric of spacetime stretches, altering the distances between particles and atoms. Over time, this could lead to a universe so vast that even the fundamental forces holding matter together may weaken. Atoms themselves might become unstable, breaking apart into subatomic particles. The structures we take for granted, stars, planets, and even the molecules that make up life, could dissolve into a sea of energy and particles, leaving behind a cold, empty void. Yet the story of the universe's fate is not without its mysteries. Could there be a way to reverse entropy, or is this destiny inescapable? Some theories suggest that in a universe governed by quantum mechanics, the rules might allow for fluctuations that could reignite the cosmos, sparking a new cycle of creation. While these ideas remain speculative, they remind us that the universe is full of surprises, and our understanding of its future is far from complete. As we ponder the ultimate destiny of the cosmos, we are left with profound questions about the nature of existence and our place within it. What does the universe's end reveal about its beginning, and how does this shape our understanding of time, space, and reality itself? What if our universe is just one of countless others, each with its own unique laws of physics and cosmic history? This is the mind-bending idea behind the multiverse theory, a concept that suggests our universe might be part of a vast, interconnected network of universes. Picture a frothy sea of bubbles, each bubble representing a separate universe, floating in an infinite cosmic ocean. Some bubbles might be similar to ours, with familiar forces like gravity and electromagnetism, while others could be radically different, governed by entirely new rules. This theory emerges from both quantum mechanics and cosmology, offering a potential explanation for some of the deepest mysteries of existence. In quantum mechanics, the concept of parallel universes arises from the idea that every possible outcome of a quantum event actually happens, but in separate, branching realities. Imagine flipping a coin. In one universe, it lands on heads. In another, it's tails. Each decision, no matter how small, could create a new universe, leading to an infinite web of realities. Cosmology, on the other hand, suggests that during the rapid expansion of the early universe, known as inflation, different regions of space could have expanded at different rates, creating isolated pockets that developed into separate universes. These universes might exist alongside ours, forever out of reach but still part of the same cosmic tapestry. The multiverse theory challenges our understanding of existence in profound ways. If there are infinite universes, does that mean there's a version of reality where every possibility has occurred? Could there be a universe where gravity is weaker or where time flows backward? These questions push the boundaries of science and philosophy, forcing us to reconsider what it means to be unique in the cosmos. The multiverse also raises questions about the fine-tuning of our universe. If our universe's constants, like the strength of gravity or the charge of an electron, were even slightly different, life as we know it might not exist. In a multiverse, this fine-tuning could be explained by the sheer number of possibilities, with our universe simply being one where the conditions are just right for life to emerge. Yet, the multiverse theory is not without its critics. Some argue that it's untestable, as other universes would be beyond our observational reach. Others question whether it's a scientific theory at all, or simply a philosophical idea dressed up in scientific language. Still, the multiverse remains a compelling area of study, offering a tantalizing glimpse into the nature of reality and our place within it. As we continue to explore the frontiers of physics and cosmology, the multiverse theory invites us to imagine a cosmos far grander and more mysterious than we ever thought possible. But how does this theory reshape our understanding of existence, and what does it mean for the future of science and philosophy? Despite all the remarkable progress we've made in understanding the universe, there is still so much we don't know. For every mystery we solve, new questions emerge, reminding us of the vastness of the unknown. Take dark matter and dark energy, for example. These invisible forces make up 95% of the universe, yet we still don't fully understand what they are or how they work. Then there's the question of the universe's ultimate fate. Will it continue expanding forever, eventually growing cold and empty? Or will it collapse back in on itself in a dramatic reversal of the Big Bang? These are questions that keep scientists awake at night, and they highlight the limits of our current knowledge. Another enigma lies in the origins of the universe itself. While the Big Bang theory provides a compelling explanation for how the universe began, it doesn't tell us why it began. What sparked that initial explosion of energy? What, if anything, existed before it? These questions push the boundaries of both science and philosophy, challenging us to think beyond the frameworks we currently have. Even within our own universe, there are phenomena that defy explanation, like the nature of black holes or the strange behavior of quantum particles. Each of these mysteries is a reminder that, despite our advanced technology and deep understanding, we are still just scratching the surface of the cosmos. This humility is essential in the scientific process. It's what drives us to keep asking questions, to keep exploring, and to remain open to new ideas. The history of science is filled with moments where what we thought we knew was overturned by new discoveries. Einstein's theory of relativity fundamentally changed our understanding of space and time, while quantum mechanics revealed a world that operates in ways that seem almost magical. These breakthroughs didn't come from being certain of what we knew, but from embracing the unknown and being willing to challenge our assumptions. Yet, the limits of human knowledge aren't just scientific, they're also philosophical. They force us to confront the nature of existence itself. What is the meaning of life in a universe so vast and complex? Are we alone in the cosmos, or is there other life out there, perhaps even more advanced than we are? These questions remind us that our journey to understand the universe is as much about understanding ourselves as it is about unraveling the mysteries of the cosmos. And so, the quest continues, driven by curiosity, humility, and the unshakable belief that there is always more to discover. How can we continue to explore these mysteries, and what tools will we need to push the boundaries of what we know even further? Technology has become our greatest ally in unraveling the mysteries of the cosmos. Over the centuries, tools like telescopes and particle accelerators have allowed us to peer deeper into space and probe the fundamental building blocks of reality. Take the Hubble Space Telescope, for example. Launched in 1990, it has transformed our understanding of the universe, capturing breathtaking images of distant galaxies, nebulae, and supernova. Hubble's observations have not only expanded our view of the cosmos, but have also provided crucial data on the universe's expansion rate, the existence of dark energy, and the life cycle of stars. Without such advanced technology, these discoveries would have remained beyond our reach. But Hubble is just the beginning. Newer instruments like the James Webb Space Telescope are pushing these boundaries even further. With its ability to observe the universe in infrared light, Webb can peer through cosmic dust to reveal the earliest galaxies that formed after the Big Bang. This allows us to study the universe's infancy, offering clues about how structures like galaxies and stars first emerged. On Earth, particle accelerators like the Large Hadron Collider are helping us explore the quantum realm. By smashing particles together at nearly the speed of light, scientists have discovered phenomena like the Higgs boson, a particle that gives mass to all matter. These groundbreaking experiments bring us closer to understanding the fundamental forces that govern the universe. Emerging technologies are also opening up exciting new possibilities. Artificial intelligence is being used to analyze vast amounts of astronomical data, identifying patterns and anomalies that might otherwise go unnoticed. Advanced simulations allow us to model cosmic events, from the birth of stars to the collision of galaxies, providing insights that complement real-world observations. Meanwhile, private space companies are developing innovative spacecraft and satellite systems, making space exploration more accessible and collaborative than ever before. These advancements don't just expand our knowledge, they inspire us to dream of what might be possible in the future. As we continue to develop and refine these technologies, we're not just exploring the unknown, we're redefining what it means to be curious. Every telescope image, every particle collision, and every new discovery brings us one step closer to answering the profound questions that have captivated humanity for millennia. But as we push the boundaries of what we can observe and understand, we must also consider the implications of this exploration. What does it mean for humanity to uncover the secrets of the universe, and how will this knowledge shape our place within it? As we gaze at the stars and contemplate the vastness of the cosmos, we inevitably confront a profound question: what is our place in this immense universe? For millennia, humanity has looked to the heavens not just for answers but for meaning. The night sky has been our storyteller, our guide, and our muse, shaping cultures, religions, and philosophies across the globe. From the ancient astronomers who mapped the movements of planets to the modern scientists unraveling the mysteries of dark matter, our curiosity about the universe has been a driving force in our evolution as a species. This pursuit of understanding is more than just a scientific endeavor, it's deeply personal. When we learn that the atoms in our bodies were forged in the hearts of ancient stars, we're reminded of our connection to the cosmos. The same forces that shaped galaxies and planets also shaped us. This realization can be both humbling and empowering. It reminds us that we are not separate from the universe, but an integral part of its grand tapestry. Every time we look through a telescope or study the behavior of particles, we're not just exploring the universe, we're exploring ourselves. The emotional impact of this journey is profound. It evokes a sense of awe, wonder, and sometimes even insignificance. Yet, it also sparks a sense of belonging. To know that we are made of stardust is to understand that we are participants in an ongoing cosmic story. This knowledge can inspire us to think beyond our immediate concerns and consider our role in the broader context of existence. It invites us to reflect on our responsibilities, not just to each other, but to the planet we call home and the universe that sustains us. Philosophically, our exploration of the cosmos challenges us to rethink our assumptions about reality. It forces us to confront questions that have no easy answers. Are we alone in the universe? What is the purpose of existence? How do we define meaning in a universe that seems so vast and indifferent? These questions may not have definitive answers, but their pursuit enriches our lives. It encourages us to embrace uncertainty, to appreciate the beauty of the unknown, and to find meaning in the act of seeking. This journey of discovery also has practical implications. As we uncover the secrets of the universe, we gain insights that can improve life on Earth. Advances in space technology have led to innovations in medicine, communication, and environmental science. The challenges of space exploration, building sustainable habitats, harnessing new energy sources, and overcoming the limits of human endurance push us to develop solutions that benefit humanity as a whole. In this way, our quest to understand the universe becomes a catalyst for progress. But perhaps the most profound impact of this journey is how it shapes our collective future. As we learn more about the cosmos, we're reminded of the fragility and preciousness of our planet. The same forces that created the universe also created the conditions for life to flourish here. This awareness can inspire us to protect Earth, to cherish its biodiversity, and to work together to address global challenges. It can also motivate us to dream of new frontiers, whether that means colonizing other planets or finding ways to coexist harmoniously with the natural world. Ultimately, our place in the universe is not just about where we are, it's about who we are and who we can become. As we continue to explore, we're not just discovering the cosmos, we're discovering our potential. The universe is vast, but so is our capacity for curiosity, creativity, and connection. How can this knowledge shape our future? By reminding us that we are both explorers and creators, participants in a story that is still being written. The search for extraterrestrial life is one of the most captivating and profound questions humanity has ever asked. Are we alone in the universe, or is life a common occurrence, scattered across the cosmos? This question has driven scientists, philosophers, and dreamers for centuries, and today, we're closer than ever to finding an answer. The quest begins right here in our own solar system, with missions like the Mars rovers diligently scouring the red planet for signs of past or present life. These robotic explorers are equipped with tools to analyze soil, rocks, and even the atmosphere, searching for chemical signatures that could hint at biological activity. But Mars is just the beginning. beyond our solar system, the discovery of thousands of exoplanets, worlds orbiting other stars, has expanded the possibilities exponentially. Some of these planets lie within the habitable zone, the region around a star where conditions might allow liquid water to exist, a key ingredient for life as we know it. The implications of discovering extraterrestrial life are staggering. It would fundamentally alter our understanding of biology, philosophy, and our place in the universe. For instance, if microbial life were found on Mars, it could suggest that life is a natural outcome of the right conditions, increasing the likelihood that it exists elsewhere. On a broader scale, finding intelligent civilizations would challenge our assumptions about uniqueness and rarity, potentially leading to profound shifts in how we view ourselves and our responsibilities as a species. But the search isn't just about the discovery itself, it's about what it means for humanity. It's a testament to our curiosity, our drive to explore, and our desire to connect with something greater than ourselves. Yet, the search is not without its challenges. The vast distances between stars make direct exploration nearly impossible with current technology. Instead, we rely on indirect methods, like studying the atmospheres of distant planets for signs of oxygen, methane, or other gases that could indicate biological processes. Projects like SETI, the search for extraterrestrial intelligence, listen for radio signals or other communications from advanced civilizations, scanning the skies for whispers of life beyond Earth. These efforts require patience, precision, and a willingness to grapple with uncertainty. After all, the universe is vast, and the silence so far doesn't necessarily mean we're alone. It might simply mean we haven't yet learned how to listen. The search also raises ethical and philosophical questions. How would we respond if we discovered life beyond Earth? What if that life is intelligent? How would it change our society, our religions, and our sense of identity? These questions remind us that the search for extraterrestrial life is not just a scientific endeavor, it's a deeply human one, intertwined with our hopes, fears, and aspirations. It challenges us to think beyond our planet and consider our role in a potentially much larger cosmic community. As we continue this search, we're reminded of the incredible complexity and diversity of the universe. Whether we find life beyond Earth or not, the journey itself is a testament to the boundless curiosity and ingenuity of the human spirit. It's a journey that unites us, transcending borders and cultures, as we collectively seek answers to one of the most profound questions of all. But what if, after all this searching, we discover that we are alone? What would that mean for us and for the universe we call home? The question of why we exist is one that has echoed through the ages, whispered by philosophers, scientists, and dreamers alike. It's a question that transcends cultures, eras, and disciplines, touching the very core of what it means to be human. From the scientific perspective, our existence can be traced back to the Big Bang, the formation of stars, and the intricate dance of particles that eventually led to life on Earth. Yet, while science explains the how, it often leaves us asking why. What is our purpose in this vast, seemingly indifferent universe? This is where philosophy steps in, offering a space to explore the deeper layers of meaning behind our existence. One perspective comes from existentialism, a philosophy that suggests life has no inherent meaning. It's up to each of us to create our own purpose. Think of it as a blank canvas. The universe provides the materials, but we hold the brush, deciding what to paint. This idea can be both liberating and daunting. On one hand, it means we're free to define our own paths, to pursue what brings us joy and fulfillment. On the other hand, it places the weight of responsibility squarely on our shoulders. There's no cosmic blueprint to follow, no predetermined destiny guiding us. It's all up to us. Another perspective comes from the concept of interconnectedness, often found in Eastern philosophies and modern ecological thought. Here, the meaning of existence isn't found in individual pursuits but in the relationships we share with each other, with the planet, and with the universe itself. Imagine the universe as a vast tapestry with every thread representing a person, a star, or a molecule. Each thread is unique, yet it's the connections between them that create the whole. In this view, our purpose is to nurture these connections, to contribute to the harmony of the cosmos, even in small ways. Science, too, offers a kind of purpose, though it's more subtle. Carl Sagan famously said, "We are a way for the cosmos to know itself." This idea suggests that our existence is part of a grand process of self-discovery. Through us, the universe can contemplate its origins, marvel at its complexity, and even question its future. It's a humbling thought that we are not just passive observers of the cosmos but active participants in its unfolding story. Yet for all these perspectives, the question of existence remains deeply personal. It's something each of us must grapple with in our own way. For some, meaning is found in relationships, in the love we share with family and friends. For others, it's in creativity, in the act of building, writing, or inventing. And for many, it's in the pursuit of knowledge, in the unending quest to understand the universe and our place within it. How, then, do we reconcile these grand questions with the day-to-day realities of life? Perhaps the answer lies in finding a balance between the cosmic and the personal. While it's awe-inspiring to ponder the universe, it's equally important to find meaning in the small moments, the warmth of the sun on your face, the laughter of a child, the satisfaction of a job well done. In these moments, the vastness of the cosmos becomes tangible, something we can touch, feel, and experience. They remind us that, while the universe may be immense and mysterious, it's also deeply interconnected with our lives, shaping and being shaped by every choice we make. As we continue to explore these questions, we're reminded that the search for meaning is not a destination but a journey. It's a journey that invites us to look inward, to reflect on who we are and what we value, while also looking outward, to marvel at the wonders of the cosmos. And in that balance, we may just find the answers we're seeking, or perhaps the questions that will guide us forward. Science and spirituality, at first glance, might seem like two opposing ways of understanding the world. Science relies on observation, experimentation, and evidence, while spirituality often draws from intuition, faith, and inner experience. Yet, when it comes to the universe, these two paths often converge in unexpected ways. Both seek to answer the same fundamental questions. Why are we here? What is the nature of reality? And how do we fit into the grand tapestry of existence? These shared questions reveal a deeper connection between the two, one that transcends their differences and invites us to explore the harmony between them. Consider the laws of physics, for instance, the intricate balance of forces that govern the cosmos: gravity, electromagnetism. The strong and weak nuclear forces seem almost too perfect to be random. This precision has led some scientists and spiritual thinkers alike to marvel at the universe as if it were designed with intention. Albert Einstein once described his sense of awe as a cosmic religious feeling, a recognition of the profound order underlying reality. Similarly, many spiritual traditions speak of a universal intelligence or divine plan that guides the cosmos. While the language differs, the sentiment is strikingly similar, a reverence for the complexity and coherence of the universe. Take the concept of interconnectedness, another area where science and spirituality overlap. Quantum mechanics has shown that particles can be entangled, instantaneously affecting one another regardless of distance. This phenomenon hints at a universe where everything is deeply connected, a notion that resonates with spiritual teachings about the unity of all things. In Buddhism, for example, the idea of interdependence emphasizes that nothing exists in isolation. Every action, every being, is part of a larger whole. This parallel invites us to consider whether the universe is not just a collection of separate objects but a single, interconnected system. Even the Big Bang, the scientific theory of the universe's origin, finds echoes in spiritual narratives. Many creation myths describe the universe emerging from a single point or source, much like the scientific model of an expanding cosmos. The Hindu concept of Brahman, the ultimate reality from which all things arise, mirrors the idea of a primordial singularity in modern cosmology. These similarities don't prove that science and spirituality are saying the same thing, but they do suggest a shared human impulse to understand where we come from. The awe inspired by the universe is another common thread. Whether it's a scientist peering through a telescope or a meditator gazing at the stars, both are struck by the vastness and mystery of existence. This sense of wonder drives exploration, whether it's through scientific discovery or spiritual inquiry. It reminds us that the universe is not just something to be studied, but something to be experienced, a source of endless fascination and inspiration. By bridging the gap between science and spirituality, we gain a richer understanding of the universe. Science reveals the mechanics of how things work, while spirituality offers a framework for why they might matter. Together, they invite us to see the cosmos not just as a collection of objects, but as a living, evolving story, one in which we play a vital role. As we continue to explore this intersection, we might find that the answers we seek lie not in choosing one path over the other, but in embracing the insights both have to offer. And with this understanding, how might we shape our future as a species? Humanity's journey beyond Earth is no longer the stuff of science fiction. It's a tangible goal, one that scientists, engineers, and visionaries are actively working toward. The dream of exploring and even inhabiting other worlds is fueled by both necessity and curiosity. As our population grows and our resources dwindle, the idea of expanding beyond our planet becomes increasingly urgent. But it's also driven by something deeper, a desire to push the boundaries of what's possible, to answer the age-old question of whether we're alone in the universe, and to ensure the survival of our species in the face of potential global challenges. Mars has long been the focal point of this ambition. With its relatively close proximity and similarities to Earth, it's often seen as the next logical step in our cosmic journey. Missions like NASA's Perseverance rover and SpaceX's ambitious plans for crewed flights have brought the red planet into sharper focus than ever before. These projects aim not just to explore but to prepare for eventual human settlement. Imagine a future where cities on Mars are as common as cities on Earth, where greenhouses grow food under alien skies, and where humans walk on Martian soil as casually as we walk on our own. It's a vision that's closer to reality than many realize, but Mars is just the beginning. The moons of Jupiter and Saturn, particularly Europa and Enceladus, offer tantalizing possibilities. These icy worlds are thought to harbor vast oceans beneath their surfaces, raising the possibility of extraterrestrial life. Missions to explore these moons could revolutionize our understanding of biology and the conditions necessary for life to thrive. Beyond our solar system, the search for exoplanets, worlds orbiting other stars, has already uncovered thousands of candidates, some of which might be habitable. The idea of interstellar travel, once relegated to the realm of fantasy, is now being seriously considered by scientists and engineers. Advancements in technology are making these dreams more achievable than ever. Reusable rockets, like those developed by SpaceX, have drastically reduced the cost of launching payloads into space. Innovations in life support systems, radiation shielding, and sustainable energy sources are paving the way for long-duration missions. Artificial intelligence and robotics are also playing a crucial role, from autonomous rovers to systems that can assist astronauts with complex tasks. These technologies are not just tools, they're the building blocks of a future where humans can live and work in space, yet the challenges are immense. The human body isn't built for long periods in zero gravity, which can lead to muscle atrophy, bone loss, and other health issues. Radiation from cosmic rays poses a significant risk to astronauts traveling beyond Earth's protective magnetic field. And then there's the psychological toll of isolation and confinement, especially on missions that could last years or even decades. Creating self-sustaining habitats that can support human life far from Earth requires solving problems we've never faced before, from producing oxygen and water to growing food in alien environments. Economic and ethical considerations also come into play. Who will fund these missions and who will benefit from them? Space exploration has historically been driven by governments, but private companies are increasingly taking the lead. This shift raises questions about ownership, equity, and the potential exploitation of extraterrestrial resources. How do we ensure that the benefits of space exploration are shared by all, rather than concentrated in the hands of a few? And as we venture further into the cosmos, how do we balance our ambition with our responsibility to protect other worlds and any life they might harbor? Despite these challenges, the potential rewards are too great to ignore. Becoming a spacefaring civilization would mark a turning point in human history, one that could redefine our place in the universe. It would open up new frontiers for scientific discovery, economic development, and cultural exchange. It would also serve as a reminder of our ingenuity and resilience, our ability to overcome obstacles and achieve the seemingly impossible. As we look to the future, the question isn't just whether we can overcome these challenges, it's whether we have the courage and vision to try. And with that in mind, what will it take to make this dream a reality? The path ahead for humanity's exploration of the universe is filled with both profound challenges and extraordinary opportunities. On one hand, the technological hurdles are immense. Space travel demands precision and innovation at a level that pushes the boundaries of human capability. For instance, the vast distances between stars require propulsion systems far beyond what we currently possess. Even within our own solar system, the harsh environments of other planets and moons pose significant obstacles. Mars, for example, has a thin atmosphere and extreme temperature fluctuations, making it a hostile place for human habitation. Developing habitats that can shield astronauts from radiation, provide sustainable food and water, and withstand the rigors of alien landscapes is no small feat. Yet, these challenges are also catalysts for ingenuity, driving advancements in materials science, robotics, and artificial intelligence that could revolutionize life on Earth as well. Ethical considerations add another layer of complexity to this journey. As we venture beyond our planet, questions arise about our responsibilities toward other worlds. Should we terraform Mars, altering its environment to make it more Earth-like? Or should we preserve it as a pristine scientific laboratory, free from human interference? The potential discovery of extraterrestrial life, even in microbial form, would raise even more profound ethical dilemmas. How do we interact with other life forms without causing harm or disruption? These questions force us to confront our role as stewards of the cosmos, balancing our ambitions with a sense of moral duty. the economic implications of space exploration are equally significant. Historically, space programs have been funded by governments, but private companies are increasingly taking the lead. This shift opens up new possibilities for innovation and investment, but it also raises concerns about equity and access. Will the benefits of space exploration be shared widely, or will they be monopolized by a few powerful entities? The extraction of resources from asteroids or other celestial bodies, for instance, could alleviate shortages of rare materials on Earth, but it could also lead to new forms of inequality or conflict. Establishing frameworks for fair and sustainable use of extraterrestrial resources will be essential to ensure that space exploration benefits all of humanity. Despite these challenges, the opportunities are vast and inspiring. Expanding beyond Earth could alleviate pressures on our planet's finite resources, providing new avenues for energy, minerals, and living space. It could also spur technological advancements with applications far beyond space travel, from medical breakthroughs to environmental solutions. Moreover, the pursuit of space exploration unites us in a shared sense of purpose, transcending borders and differences. It reminds us of our common humanity and our place in the cosmos, fostering a sense of wonder and curiosity that drives progress. As we look to the future, what lessons can we take from the universe's journey? Perhaps it is that challenges are not barriers but invitations to innovate and grow. The universe itself, after all, emerged from chaos, evolving into the intricate and awe-inspiring tapestry we see today. In the same way, our exploration of space is a testament to our resilience, creativity, and determination. It is a reminder that the path ahead, though difficult, is filled with the potential for discovery and transformation. And as we take these steps into the unknown, we carry with us not just the tools of science and technology, but the enduring spirit of exploration that defines us as a species. From the explosive birth of the universe in the Big Bang to the intricate dance of particles forming atoms, and from the silent pull of gravity shaping galaxies to the emergence of life on a small, blue planet, we've journeyed through the cosmos to uncover how the universe builds itself. Each step we've taken through dimensions, quantum realms, and the vast cosmic web reveals a universe that is not random but profoundly interconnected. Every atom in your body was forged in the heart of a star, and every force that holds matter together echoes the first moments of creation. This is a universe that builds itself layer by layer, from the tiniest quark to the vastest galaxy, in a process both elegant and mysterious. But this journey is not just about understanding the cosmos, it's about understanding ourselves. As we explore the universe, we are also exploring the very essence of our existence. We are stardust shaped by the same forces that shape the galaxies, and our curiosity drives us to uncover the secrets of the cosmos. This quest for knowledge is what makes us uniquely human. It's a reminder that we are not separate from the universe but an integral part of its story. As we gaze at the stars, we are looking back at our origins and forward to our potential. The universe is a testament to the power of connection. From the smallest particles to the largest structures, everything is linked in a delicate balance. This interconnectedness is not just a scientific concept but a profound truth about the nature of existence. It teaches us that we are all part of something greater, and that our actions ripple through the fabric of reality in ways we are only beginning to understand. As we continue to explore, we are not just discovering the universe, we are discovering ourselves. Each new insight, each breakthrough, brings us closer to understanding our place in the cosmos and the incredible journey that brought us here. So let's stay curious, let's keep asking questions, seeking answers, and marveling at the wonders of existence. The universe is a story still being written, and we are both its readers and its authors. Share your thoughts, keep wondering, and remember, the journey of discovery is never over.